Hello everyone, we are Group 1. My name is Hao Duanjiang. The other two group members are Tian Yizheng and Deng Yipan. This is our group project final presentation. So our design for the processor, we use the 5-stage RSD pipeline. This is a very classic pipeline design used for the processor. It has 5 stages, which are instruction fetch, instruction decode, execute, memory access, and write back. Also, we include all the 5 individual components there. It's very easy to track it down since we name all the individual components as what it's supposed to be. And as you can see on the right hand for the picture, we have all the 5-stage structure and all individual components with it. Also, when we try to put them all together, we find out the processor is just used for the operation stuff, and the memory is actually different. So when we are run the test bench to test our processor, we put the memory inside the test bench, not in the processor.
I wrote a test bench for some individual components. I'm gonna explain the idea of each test bench. Yeah, so for the test bench of ALU, it gives the value of x and y and the type of the operation and compares the output to the desired value. So for the test bench of control unit, it gives the value of instruction data and check if the type of ALU operation and the memory operation are correct. So the test bench for instruction and data memory, it gives the memory address and its operation type and checks the value of data memory. So, and the test bench of RC register is just like what we did before with respect to counter. It checks if the counter of RC register works correctly. The test bench for register file first provides sets of 32-bit data and its address, and gives the address of RS1 and RS2 and checks if the output of RS1 and RS2 matches the desired value. So yeah, so this is a simulation of ALU test bench, and yeah, it succeeded.
I will mainly explain our complex program and the processor's simulation. I wrote an RC5 simple function encode part with RISC-V assembly and divided it into 2 parts. The first part is the data memory initialization, and the second part is RC5 encode. I used the simulator below to test the assembly code and then converted it into machine code by using the method inside the website. Here is my assembly code. The first part is the ROM initialization, and the second part is a simple function encode. First, let's test it in the simulator. However, there is a slight difference between this one and the one we implemented in the class. Since I used the logic left shift replacing the left rotation, so that the result will be slightly different. But if the result in the simulator is the same as it work in the processor, it will also prove the processor's functionality. Let's run it. In this assembly code, I do store the result of the encode to the data address of 0x100000 and 0x100004. So these two lines are the final result. Also, because our processor's data memory begins at the address 0x08000, it's a different with the simulator. So when before converting it into machine code, I should change the data address to 08. And then convert it into machine code. And then we can simulate in the Vivado. In the processor test bench, it will first read the instructions from a file named instruction memory test file .hex, and it will execute the instructions sequentially. So we should paste the machine code into this file. We have done it before, so I need not to do it again. Then run the simulation. As we can see, the instruction memory recorded all the instructions sequentially, and the data memory recorded the S key, which is a secret key, and the first two elements of the data memory is the result we stored. And find the last instruction, which is here, and we can see the data memory. The first two elements of the data memory is 11.5D, 8E, 7080, 632E, and which is the same as in the simulator here. So that the processor can work correctly. That's all. Thank you.